Hello everyone. We are just going to start off with differential geometry today. So we've completed a lot of extent of complex analysis, like explaining key results and all that. Now from on one side, once like analysis is done, the next step begins the exploration of differential equations. So I'll be, of course, I'll be skipping over the basics of differential equations and calculus and all of that, and then moving on, just starting off with differential geometry. The idea behind differential geometry is essentially the motivation is essentially that when you talk about a differential equation, let's consider two kinds of equations, right? One is so on one hand you have the Laplacian. This is basically this is one kind of differential equation, and on the other side let's take or something like that, right? So this, when you look at these two differential equations, the first thing that you notice is this occurs directly in physical situation, whereas this doesn't occur directly in physical situation. More, if you're ever solving this equation, it will be mostly to get yourself familiar with the techniques in mathematics for pure mathematical purposes, right? So just for the sake of solving problem, right? You won't most likely won't encounter this kind of differential equation on product. Okay. And just change the order here. So you have the Laplacian here, and then you have like a differential equation of two variables with two different orders. That's the idea. So most generally, when you're dealing with sort of analytic differential equation, you want to find out some problem or some kind of a system which is what do you say, for the lack of any better word, better phrase, for something which is geometrically simple or perceivable. Right? For example, when we look at waves on a string, we immediately model it with sine and cos waves. So we just don't like, so that's the first thing, right? So when you have this kind of when you have this kind of an equation, the sine and cos solutions are the first solutions that you study in some kind of a system. So the idea here is that when you are trying to navigate nature, you start with something simple first. You start with some sort of like building blocks, and you look at sets, or you look at any object that can be mapped to simple ideas or simple geometric shape. For example, the circle, and then after the circle you have the unit circle. Then you have the sphere. Then a modification of the circle is the cylinder. So you have the cylinder like S1 into R, and then you have S1 into S1, which is torus. So you have simple modification and modifications of simple objects, which are mostly considered for putting your functions into that. So in this process, right, as I'm talking about these things, the first there are a few steps. The first, of course, is to understand how you're modeling this into this kind of a system into geometry, right? How are you reducing this kind of a shape into a geometry shape? That is the first thing to actually talk about. And then we can, like, along with that, we need to get ourselves acquainted with some terminologies that will just help us in geometry, right? So, right. So, and one more thing to notice is, so in most physical systems, so you have certain simple formulae or certain simple equations which give you or which are like extremely fundamental, right? For example, given that we deal with most of the time we are dealing with some semi-Riemannian manifold. Like we come to talk about what that is exactly later on. But given that like most of your physics is built on either Euclidean manifolds or you have the semi-Riemannian manifold. So based on this very simple assumption, right? So you have certain strong properties of these particular manifolds, right? So the idea is to, in the long run, explore what these properties are, along with looking at how these manifolds work and what exactly we are trying to do here. So as I said, the end goal of the whole thing is to reduce complex physical system into simple geometric objects and map it to simple geometric objects. So now, so for example, like the equation, the strong conditions that I'm talking about, for example, the lead derivative along a axis of symmetry is 0. Lead derivative of the metric. So this is the metric of manifold. We'll come to that later. But the lead derivative along the metric along an axis of symmetry is 0. That means that if you have some sort of curvature, right? Any like kind of curvature will have some sort of an axis of curvature where there is like it's flat essentially. So for example, if you try to fold a sheet of paper into roll it into a cylinder, like every line on the cylinder will be like it doesn't bend, right? So the lead derivative along this line of the metric, so the metric gives you a measure of the distance. So for example, if it is a straight line, the metric doesn't change. So when you have like a unit metric, but then if it is curved, your metric changes. So the metric is basically a measure of curvature, how things are curved. So from and it comes from your Pythagoras theorem. So we look into all of that later. But the idea is, so along this line, there's no curvature. So you're saying that the lead derivative. So if you take an infinitesimal vector here, in this, like in the vertical direction, the lead derivative along that of the metric will be 0. So basically there is no curvature. And then another simple fact is so another simple fact is that the Laplace is equal to 0. So basically the Laplacian of say the second derivative of the metric will be 0. So it gives you this equation actually gives you your Jacobi fields. So we will talk about that later. It's got to do with your tidal forces. So basically when you take the Laplacian, you go to the second order. That means your So when you fix a frame of reference and then you have like you have a moving frame, and you basically need to observe a moving frame from a static frame, moving in the sense accelerating frame in this case, because the second order of derivative that comes in. So you have an accelerating frame and then you have a stationary frame, and in order to correct the forces experienced by the accelerating frame, first the acceleration has to be taken into account. That's what gives you the pseudo force. So basically it tells you that once you put the pseudo force into scope, and the ablation of the metal band. So essentially for a free fall, there is no real acceleration, right? So there is only acceleration on some sort of with respect to the frame of reference, but there is no real absolute relative acceleration. So under free fall, under gravity. So you should see how those terms cancel out sometimes. So anyway, so and then you don't have the Noether's theorem. So these are actually in some way so in some way some forms of Noether's theorem. So we'll come across it later. So at the end, the goal will be probably to study this kind of basic constraint and to see what we can make sense of. So why these constraints and why like differential geometry, again the lead derivative, the concept of your Laplacian, these are based on simple geometric concept. So like I said, lead derivative is an invariant, like along a particular vector. So you have a straight line, and if there is no curvature, the straight line continues to be a straight line. So the lead derivative is essentially 0 here. And then similar with the Laplacian, we'll look into this as we move along. But this is the primer, so probably a motivation to call it as to why we want to study differential geometry. So again, at the end of this particular lecture today, so we'll just go through some preliminary concepts or idea, and then we'll move on to like a little bit of other description of terminology. So again, there are two notes that I want to give. From personal experience and studying differential geometry, there are two things, okay, that I've observed. So first is the learning of what these symbols are, like symbolisms used and formalisms used in differential geometry vary extremely. So some are like, so some people like, especially if you're tending towards topology, you want to get rid of all the external like, you know, indices and all of that, and then you just want to write down something very simple, something very abstract in the sense that I wrote right now. So you just want to get away all like your extra symbols, additional work and everything, and present things in terms of very pure and simple object. While this gives you an understanding of the concept, it, like, I personally faced a lot of difficulty when it came to actually putting and solving problems. So for example, the simple idea of like the Levi-Strauss symbol and the cross product. Okay, so you'll encounter that later, and how the indices change, and then how the signs and all of that. That was not very apparent when you go through that route. But on the other route, when you have like all the indices written down, everything explained, then it becomes extremely cumbersome to, you know, like learn the whole thing, because there are so many variable changes, so many things that you need to keep track of. So in going through an example itself becomes somewhat tedious. So that's just one note on symbolism. Second note is, as far as possible, again, because this is a mathematical subject, right? So although heavily used in physics, it is still rooted in mathematics based on certain mathematical assumptions. So it is extremely important to be aware as you go along further into the subject. It becomes important to be aware of what the mathematical I have like an link or I have I have an idea that probably the assumptions changing in the mathematical structure, change in the assumptions in the mathematical structure of physics can probably lead to new understanding, if not like the solution, direct solution of current problem that trouble all physics. It leads to a new perspective or new understanding. So, for example, the transition from Euclidean geometry to Riemannian geometry, and like the integration of time, space-time, right? So that gave you your transcended your classical mechanics or your Newtonian mechanics into your the realm of general relativity. So such idea, just pay attention. Just be I don't know. Just try to be aware of what the assumptions are, because as we go along the subject, because there is so much to do and so much to learn, you most often end up forgetting these assumptions. But then later it's very important to just come back and then see what your assumptions and how you can tweak it around to make something more meaningful. So anyways, with that we'll just start off for today. The first idea that I want to convey is is what equations are and how they can be reduced to geometric object. So, for example, so we'll look at do you know what your N is, right? Is the Euclidean manifold of n dimension. So, for example, so it's basically written as x1, xn. So this means a few ideas here. First, that Rn is composed of n independent sets, n independent objects. It's a set of n independent objects, and each independent object constitutes an independent dimension, and each dimension can be represented by a basis. So x here, x1 is okay. So x1 can be further written down in terms of say some sort of a1, e1, right? So a coefficient and a basis. So if we talk about e1 is basically e1 is a basis. What is a basis? It's a unit. So you're taking a unit vector in that particular direction, and then you're plotting a basis. So obviously you have your results for your orthogonal basis and all of that comes in your vector calculus, vector analysis and all that. But essentially, so the idea here that needs to be conveyed is that your Euclidean n set it can be decomposable, it can be decomposed into a basis, particular some sort of basis. So when and why this basis? So let's look at so this is the most general basis that we have, the most general set that we have. We're just saying that we have n independent number. So we have a space of n dimensions, and then geometrically just like one point in that space of n dimensions. So now let's add a constraint. Okay. So it's not one point, it can be any point. So it's the entire space of point. So let's just add a constraint, which is E of R is equal to L square minus R square minus L square is equal to 0. So basically, you are constraining the whole thing into just saying that from a particular origin, from a particular 0 point, you are saying that the length of each point is uniform. So this is basically, so this equation is basically it can be written down as x square plus y square plus z square minus L square is equal to 0, which is s okay, yeah, first of all, like if this is S2, so you have like a three-dimensional, like a sphere, the surface of a sphere in 3 dimensions. So first, okay, so from Rn, just keep in mind that we're talking about a subset of Rn, which is R3, that is equal to x, that is basically composed of x, y, z. So these are the variables, so the 3 variables that we are dealing with, and this particular constraint is basically gives you S square, which is a subset of R3. Right. So now the next step, let's add one more constraint. The other constraint will be that you are restricting it to a single place. So you are taking some so you either take either x to be 0 or y to be 0 or z to be 0. Right? So this is the second constraint, and then you have S1, which is a subset of S2, which is a subset of R. So now from any point in the space, you have reduced the whole system to a single, like a point on a sphere, and then you have further reduced it to a point on a circle. So this gives you the idea of what topological like objects like are, and how as you see, this is a submanifold of R3. S2 is a submanifold of R3, and S1 is a submanifold of S2. So basically, so given this geometric interpretation, so we look at the definitions that we'll try to get a little more clarity on what manifolds and what mapping and what we'll build a heavier, stronger foundation to talk about it. And later we'll see that most physical objects are some sort of a subset of some sort of a sphere, or like a combination of a sphere and a real number. So for example, you have your topological the topology of like certain like extremely interesting object can often be reduced to S2 times S2 or S1 times S1. This is a torus, by the way. So or S1 times R, which is a cylinder. So you have certain, you have your extended object, extended shape of different dimensions coming together because of certain simple shape. So we'll just look into all this. In fact, your groups or your equations of the kind of functions or the kind of translation or the kind of mapping that happens when you move an object, right? In Newtonian, under a force or under constant velocity or something like that, often present some sort of a topological object. We'll see what this is, because your velocity gives you is a subset of something, and like it's not like it can be mapped out topologically. So we're looking at all of that, all of like fluid theory and all of that basically. But the idea that I want to get across is like this, right? So you have the more the number of equations, the more the constraints of your general bit set that you're taking. So the more the number of equations, so you're further and further simplifying a particular problem. So obviously, so if you have again, then if you specify your theta after this, okay, so which is say x by y is equal to some constant, you have a particular point which is a subset of S1, which is a subset of S2, which is a subset of R. So this is a point solution. So you have a particular exact solution, right? So now, given this, actually you do have two solutions in this, because your x the axis gives you a line, and then through the line gives you 2 points in circle. But essentially, what I'm trying to say is that you have a geometric reduction of your base problem. So now, given this, like just forget all of this. We will start off with some sort of like definition. The first idea is that again, so all of this was geometry. Now coming to the part of differential, to the idea of in the sense of differential geometry. So why do we have differential? Because we see certain geometry creeping up when we talk about your differential and integral operation. So essentially, so to get to that point later, we just look into, we just come and we just define some a transformation or a mapping. So let's take R and map to R M such that N is greater than M. Right? So when we look at a certain mapping from Rn to Rn, such that the dimension of the initial manifold is greater than the dimension of the transform manifold via some sort of mapping of gamma. So now gamma is more often your differential operator. So because when you reduce, so how do you remove or how do you take away one variable from like if you have n variables and you want to remove one variable, how do you do that? Differentiate. So for example, if you have some linear, some simple function x plus y plus z, right? So when you take this, differentiate with respect to say dou by dou x plus dou by dou y times this. Okay. So times that. So when you try to apply this operator, so what you have is you have 1 here plus 0 0, and then you have plus 1 more here. So you have to essentially, right? Okay. And in this case, it's a very simple function. So you basically reduce the whole thing because of the constraint that I already spoke about, because of the constraints that come in the form of this equation itself. And then you have the second constraint. So actually you have two constraints. So it reduces from 3 dimensions to just one number. So one dimension to just one number. So so when we have more complicated functions, say for example x squared or y So when you try to do this, note that your like the power, the exponentiation when you differentiate is essentially decreasing. This is the tool that we will basically use when you're trying to convert a subset of equation. So you can do, the idea here is you can do this by talking about normal normal equation which are linear equation, but when you insert an operator, it becomes much more powerful because of the analyticity involved here. So when it comes to differential structures, so then we can, and also differentiation observes some algebraic properties that we know. So we can take advantage of those as well as linearities and certain advantages of those properties as well in order to reduce the problem, or rather give a more dynamic structure to the physical problem that we have. So let's just so basically when we look at this, so we talk to this kind of differentiation happening n times. So if it is a function that can be differentiated with this, and note that this is not, it's not Rn or Rm that is being differentiated, it is rather the function here that is being differentiated. So when your function you get differentiated every time, you call that a class, an n class. So nth analytic class. So for most of the time we are dealing with Hausdorff manifold. So essentially, analytic manifold. So essentially, you have unless it is specified, you have functions that are infinitely differentiable, that are analytic no matter how many times you differentiate it. So, for example, functions like the sine and the cos and combinations of those functions. So, essentially, now let's talk about. So, if you have a function of class R, so it's defined as a mapping from Rn to Rn. So you have again, you have an dimensional object, and then you have a function that takes it from a dimensional object to a dimensional object. This is a more general example, and also I was trying to give idea of like kind of reduction of dimensionality and those kind of things. So which is why I just brought that example. But essentially, this any function of belonging to R, any functions that belonging to gamma are functions of class R. So as specified the class of gamma here. So gamma is the set of all the functions of class R that can take an n-dimensional Rn to Rn. Now, so if you have a function that is of class S such that gamma S such that S is lesser than R, then gamma S is a subclass of gamma. It's a sub-pseudo group of gamma. So it's like this basically gives you a function which are less time differentiable. So nothing extremely important, extremely important except for terminologies and some sort of sense of what is happening. But the real thing, the real advantage when it comes to differential geometry is the idea of a Jacobian. Right? The Jacobian is the most visceral tool that can keep track of any sort of change that is happening. So how do we define the Jacobian? So if you have a function, it can be decomposed into n bases. So Jacobian is basically if you have a function f, if you have some function f, your Jacobian is defined as the set dou f by dou x1, the vector or the matrix dou f by dou x2, so on, dou f by dou xn. Okay, what does it give you? Basically, the Jacobian tells you if you are mapping a variable, if your f is defined in such a way that it takes you from y to x, it changes your variables from y to x, then the change in the variable y can be tracked by your Jacobian. So basically, when you it's like imagine a function, imagine some sort of a function here, right? Or rather than talking about function, let's talk about coordinate axis, like coordinate bases. So for example, if you have x1 and x2, and then you have some sort of y1 and y2, which is an angle. So when you transfer from your polar to Cartesian coordinate or vice versa, you have a Jacobian for that. So you're basically, how you're measuring this is you're mapping x1 to y1, and you're mapping x1 to x2 to y2, and you're mapping you're doing all sorts of permutations and combinations to figure out exactly how each basis is changing to each basis. So for example, if you take a simple rotation, okay, if you take a simple rotation of or like some sort of squeezing, so this gives you the Jacobian. So this gives you, so this the Jacobian here dou x 1 by dou y1 will be 0. However, dou x1 2 by dou y and dou x2 by dou y2 will not be 0. So essentially it gives you some sort of constant indicating that the vector here has changed by a certain degree. So it has taken certain elements of what your initial, again, a little bit confusion in terms of variable per se, but essentially the idea is once you have a transformation, for every transformation there is some sort of coefficient, and that is given by the differentiation. So why exactly differentiation? We will see in a bit, right? So then obviously, so if you can decompose f into the dual of the function, so that basically gives you a matrix in terms of f1 to fn. So your Jacobian is nothing but your f1 to fn. So you can decompose the function into individual functions of like, or vectors, or like each component are giving it a basis, and the Jacobian is nothing but in time the coordinates. I mean the tangents. So once you keep this in mind, so refreshing vector calculus and keeping this in mind, we will actually move on in the next session to learn more about what this tangent vector represents and how we kind of formulate the whole thing. But one more thing that you need to take away from this is this gives you a matrix, right? The Jacobian gives you a matrix, and the determinant of the Jacobian gives you how the area has changed. Okay, so for example, this area is 1 and this area is, let's say, half the area covered by 2 unit vectors. Okay, and then this is, so obviously every time you are squeezing the unit vector, you are doing something to the area, right? So the determinant gives you the measure of how the area has to be. So this has unit 1, and then if it is non-zero, then it means that something the area has been either squeezed, right? So one thing that I wanted to think about is, can the area ever be expanded? Like, for example, if you have 2 unit vectors, can the area ever be more than a square, than the 2 unit vectors itself? So what is the largest area that you can talk about that 2 unit bases will cover? So what is the unit basis of the secondary unit basis of this vector? R theta, the R to theta doesn't really make sense. So the 2 pi, it cannot be really unit, or can it? Or your theta is not a vector in the first place. So the circle is a reduction of the Cartesian system, where you're keeping one axis constant, one thing constant, and then you just have a vector that you have one vector in the whole distance. But you can't really, do think about it, how to put down theta in terms of a unit vector and how do you convert that. But maybe that's a whole not some food for thought. But beyond that, I think this is all for today. And so next time when we start this thing, we'll be going formally into the definition of manifolds. We'll be defining tangent vectors. We'll be defining what mappings are and what pull back and all of those kind of things. And so that's it.